Hello, this is the section 1.5 lesson. In this lesson we're going to introduce what we call conditional probabilities, and then we're going to use those in what we call the multiplication rule, which is going to be somewhat similar to the addition rule that we just saw in the previous section. Okay. So first let's give an informal definition of this idea of conditional probability. A conditional probability looks pretty scary the first time you see it. The notation is P of A vertical line B, which is read the probability of A given B. A and B are both events here. And informally, this means the probability of A occurring given that event B has already occurred. So somehow we know that event B has already occurred. We want to figure out what's the probability that event A has also occurred. Okay. Now, a little more formal definition of this is given here. The conditional probability of A given B is, we can calculate this as the probability of A and B divided by the probability of B, provided that the probability of B does not equal 0. Okay? So calculating conditional probabilities is usually fairly simple. We just have to calculate the probability of the intersection, divide it by the probability of B, and we're all done. And so let's do a simple example here to illustrate how we can do this. So it says if we randomly choose a family with 2 children and find out that at least one child is a boy, find the probability that both children are boys. Okay. And so first of all, let's list our sample space here. So in a family with 2 children, we could have a boy and a boy, or a boy and a girl, or so on and so forth. So there's 4 different outcomes. And let's let A be the event that both children are boys, and B be the event that at least one child is a boy. Now, we know that event B has already occurred. Maybe we met the family and we saw one of their children, it's a boy, so we know that event B has already occurred. We want to know the probability that A has also occurred. Okay? That's the whole idea behind conditional probability. And so to calculate this, let's use our definition here. P of A intersect B divided by P of B. Here's our sample space. And so let's calculate these 2 individual probabilities on the right. Okay. So let's start with the numerator there, the probability of A and B. That's the event that both children are boys and at least one child is a boy. Well, the only way that can occur is if both children are boys. And we see that that can occur in only one way, so this probability is 1/4. Now in the denominator, P of B is the probability that at least one child is a boy. If we look at our sample space, we see that in 3 of those outcomes, at least one is a boy, and so this probability is 3/4. And so now we divide those 2 probabilities, 1/4 divided by 3/4, and we get our probability of 1/3. Okay. So what this means in a practical sense is that if we meet a family with 2 children and we know that at least one of them is a boy, there's a 1/3 chance, or a 1 in 3 chance, that the other child is also a boy. Now we can rewrite this definition of conditional probability in the form of what we call the multiplication rule. And so this says the probability that events A and B both occur in one trial of a random experiment is P of A intersect B is the probability of A times the probability of B given that event A has already occurred. So again, this rule simply comes from rewriting the definition of conditional probability and solving it for the intersection rather than the conditional probability. So what this says informally is that to find the probability that both A and B have occurred, we need to take the probability that the first has occurred times the probability that the second has occurred, given that the first event has already. And so let's illustrate this with this next example. So I'm going to go back to this scenario of the professor who gives review problems for the tests, and then he records the grades that each student gets. And so remember what we've got here is 80 students who took the test 42 of them completed the review problems, 38 did not. 46 got an A or a B, 34 got a C or below. But now instead of choosing just one student like we did in the previous section, we're going to choose two different students. So we're going to select one from the 80, and then we're going to select a second from the remaining 79. Find the probability that they both completed the problems. And so let's define some events here. Let's let A denote the event that the first student completed the problems, and B is the event that the second student completed the problems. Okay? And so we want to know the probability of A and B occurring. And so by our multiplication rule, this is the probability of A times the probability of B given A. So let's calculate these two individual probabilities on the right. Okay? So P of A is the probability that the first student completed the problems. Well, when we select that first student, there's 80 students to choose from. 42 of them completed the problems, so there's P of A. Now, probability of B given A, we have to take into account the fact that we have already chosen a student who completed the problems. So that means there's only 79 students to choose from, and out of those, 41 of them completed the problems, because we've already selected one student that completed the problems. So there's the value of that conditional probability, and now we simply multiply those two probabilities, and we get our answer of 0.272. Okay? So what this means in a practical sense is that if we were to complete this or do this random experiment a whole bunch of times, about 27% of the time we would select two students that completed the problems. Now, in our last example, we are going to combine this multiplication rule along with axiom 3 from our axioms of probability. So let's suppose we've got a bag with 3 red and 2 blue cubes, and we're going to select 2 of them without replacement. So it's like the previous example, we're going to select one cube and then a second cube, and we want to find the probability that we get a red cube and a blue cube, but not necessarily in that order. So this can occur in two disjoint ways. We could get a red cube and then a blue cube, or we could get a blue cube and then a red cube. Disjoint means that they can't occur at the same time. Okay, now that's nice because that means we can apply axiom 3 to calculate some probabilities. Okay, so let's introduce some notation. We want to find the probability of getting a red and a blue cube. And this can occur in two ways. We can get a red on the first and a blue on the second, or a blue on the first and a red on the second. And again, those are disjoint, so by axiom 3, that's the probability of the first event plus the probability of the second event. And so let's calculate these two probabilities on the right. Let's take probability of R1, B2, and so that's red on the first and blue on the second. So probability of red on the first times the probability of blue on the second, given that we got a red on the first one. So when we choose the first cube, we have 5 to choose from. 2 of them are red, so that's P of R1. Now, when we choose the second cube, there's only 4 to choose from. 3 of them are blue, so that's the probability of B2 given R1. So we do that arithmetic and we get 3/10. Now let's take the second probability, and this is calculated a very similar way. P of B1 and R2, so P of B1 times this conditional probability. When we choose that first cube, there's 5 to choose from. 3 of them are blue. When we choose the second one, there's 5 to choose from. 2 of them are red. And so we get the exact same answer as what we got there in the first part, 3/10. And so now we can get our final answer by adding those two probabilities. 3/10 plus 3/10 is 3/5, and we're all done. So what that means in a practical sense, that if we were to repeat this experiment many times, then about 60% of the time we would get a red cube and a blue cube, not necessarily in that order.